It's a continuation, the example here, of the story we have seen so far. Now we are imagining that we are having kind of a big ball here of things, and we have sort of the lower, and we have the upper. And I think I usually compute like this, that this is from, no? This is from the lower, and this is from the upper part. So we have a sample from the lower part and the upper part of the container with the mixture for the tablets. And we want to check if there is a difference in, for now at least, in the variabilities, in the heterogeneity level in the two different parts of. We could also afterwards, and we'll see if we have time for that, I'm not sure, but we could of course also compare the mean levels of the mixtures. We can compare both things, the average level of the mixtures, but also the heterogeneity, the variability of the mixtures can be compared. And we start with the topic of today, which is focusing on heterogeneity, on variances. We want to formulate the null and the alternative to check if there is a difference in the means, which was not what I was saying, of course. Did I not read everything here? Or am I just ahead of myself? Okay, yeah, I was a bit, okay, it was part of the story here. Here actually was the variance thing, and then if time, we have the mean thing afterwards. So here was the words saying that we want to compare the variances. Okay, sorry about this. So we compare the variances. The null hypothesis would be that the one variance is equal to the other variance. What about the alternative here? What is the relevant alternative? What would you say? Any obvious things here? Remember what I told you. Rules of thumb is, generally speaking, if there is no clear additional information about that it should be one-sided to either one or the other side, then go for the two-sided. It could be discussed here, but at least I think in the words, when I read the story, there is nothing in the words that indicates to me that I should assume that there is only one way that the variances could be different. Nothing, I mean, you could speculate on what it's really about, and then you might argue your case. But if you look at the story as you were told it here, as the information you were given, nothing in the words are sort of this tendency of layers. That's only for the mean values actually. So okay, it can be argued. I would say, I'm not sure about the one-sided thing at least. So if I'm not sure about the one-sided thing, I go for the two-sided. The F statistic to be used was to take the largest variance and divide by the small variance. What was the variances? They were 0.08 and 0.03 squared. What is this number? I achieved the number 7.11. The question is the fact that the one variance is 7 times larger than the other one. That sounds a bit large, right? But then again, the standard deviation is only 2 point something larger than the other standard deviation if we take the square root, right? Is that unusually large, or is that within what you could expect due to just random variability? When you sample only 9 in 1 and 12, with 9 and with 10 and 12, you have rather vague information about variability actually. But let's go check. Let's go check. One good thing about spitting on your computer is that at least that one you don't see. Now you saw how I tried to get the spit off my computer here. I know what you think. Sometimes there are information you don't want. Okay. Let's try to find out about this. Could we find a p-value? Could we find, or a critical value? We could also go for the critical value. What is the limit here? Well, the F distribution we should use, we should keep track of how many observations we have. For the 0.8, which was in the numerator, we used 12 observations, and for the other one we used 10. So the F we should use is 11.9. We do a two-sided hypothesis test. So in fact, we should find F alpha half. Let's use, I don't know if we were told. Let's just make sure that I don't contradict. I do not. We use 5%. So we should find this critical value and then see whether it's 7 is below or above this number, right? Now we get a problem, but that's interesting enough, so let's do it. There are 2 pages of numbers when we look at table 6. 6a. Zoom in a little bit. 6a are simply giving, it says F 0.05. It's simply giving 1 point on many different distributions, depending on the numerator degrees of freedom and the denominator degrees of freedom. Now we actually have an additional problem here, because we had 11 in the numerator, and that's not even told to us. We only have 10 and 12. We interpolate if we use the table. And then we had 9 in the denominator, right? So what is the 5% point of this F distribution, of the relevant F distribution? The 5% point is 3.1, right? If we interpolate here and do a rounding to 1 decimal point. Then we have seen that the 5% point of this one, 11.9, was 3.1. Actually, I'm actually going for, to finish this question, I would be going for the 2.5% to actually finish this one off. Well, that's actually not even the one I was looking at. What can I do more by using the tables? Well, I could look at the next page, page 519. In page 519, I get 1 more point on each distribution. It's very sparse information on the individual distribution. I get the 1% point now on many different Fs. So we go for the 9 again, we go for the 11 again, and the 1% point is, what's that, 37, that's, let's say 5.2 if we do to one decimal point. So we do linear interpolation. So the 1% point in the 11.9 distribution was 5.2. Can we finish the conclusion now if we wanted to? Yes, we could. Even though the table does actually not give us the table, and there are no more tables in the book. These are the 2 pages of information which are in the book regarding the F distributions. We cannot find the 2.5% critical point in the F distribution in the tables. However, it's good enough because we can see that the 7.11 is actually larger than this one, right? So if the observed F is larger than this, the 1% point, But then it's also larger than the 2.5% point, right? So we could, using the tables, come to the right conclusion that we have to reject the null. We have to reject. So we have proven that the variances are different, right? Let me just finish off by jumping into R and looking a bit on some numbers and showing you where should I go to have it in the right order, like this. Here, I should put it in. I can find, I have the QF, I can find 0.025 using 11.9. I have to put 2 sets of degrees of freedom, and I can find, and now I made the classical mistake. I should find, because it has the opposite notation, so to find the 2.5% point, I should specify 97.5% here to achieve that the 2.5% point of the F is 3.91. The 2.5% point of the relevant F of the 11.9 is 3.9, right? It doesn't change my conclusion because I already knew, of course, that the point would be between 3 and 5. So I mean, it doesn't change anything. It's just to show you that if we use R, we can find all these percentiles very easily. Then, as I planned, I will skip the comparison of the means. Actually, you would have to use the footnote of table 8.1. Why would I have to use this? Because I have proven that the two variances are not the same, right? So the two variances are not the same. So when I go and compare the means, when I want to go and compare the means versus, for instance, mu1 difference to mu2, I should, when I look at the table, focus on this situation in the middle here, which was the one assuming different variances, right? And this was the one where you had to use the dagger here, the footnote of the table. So we could do it. In fact, as I told you, this is what R does by default. If you don't ask it to do anything else, that is what R is doing for us. So it's a kind of nice thing, actually. Default in R. I want to compare one more thing in R. We are in the middle of doing the R thing also, as planned. We have these distributions in R. We have the T, we have the chi-square, we have the F. We have the densities. We mostly use these two. We actually also have the R for random simulation. We'll get back to that in 2 weeks. We use the P and the Q mostly for hypothesis testing and confidence intervals. Let's do one more very interesting thing now. I'm still referring to our heights data on U, on males and females from a couple of weeks ago. We found out that actually, if we use the t-test on this, just to, come on, yes. Just to emphasize, I have the female heights here. I had the male heights called male here. Last time I compared by applying the t-test function. Let's do it again. What I get compared if I compare the t-test function is it calls it the Welch two-sample test, meaning that it uses the footnote. That's the name of it. It uses the footnote. it gives me that males are 183, females are 170, and statistically, I'm very certain that the mean height is different between males and females. Not a big surprise, but maybe it's interesting to be so very, very sure about this fact based on this small sample that I've taken among you. However, let's try the thing that we've learned today. What about, are the variances really different? Let's compare the variance of males and the variance of females. Let's compare the variance of females with the variance of males. I put the largest variance on top. That's what I changed here, right? As we were told to do. I have that the female variance is 1.1 larger than the male variance. Whoa, that's small. I at least, that's my feeling. That's really small. That's not a big difference. Are we sure it's small? Well, we could find the p-value by taking this number, putting it into the PF, seeing whether, then we have to, do I know what the length of, we say that N1, I'm finishing in just 2 minutes, N1 is length of female, that is the number of observations, N2 is length of the males. Should we just check N1 and 2? 14 and 31. I should use N1 minus 1. I could also write 13. Now I write N1 minus 1, then it works if I change the data. N2 minus 1. PF gives me probability of being to the left. I should take the probability of being to the right because I'm above 1. And then actually I should multiply this by 2 to have both tails. And here's the p-value. Can we prove that variances are different between on males and females here with a p-value of 0.77? No. It's a very likely thing to see, as my impression also was in the beginning, to see that two variances compared to each other are like this 1.1, only a 10% thing. That's a very small deviation. It's a very likely thing. So everything is okay. We cannot prove differently. We could use the other t-test version then, but it doesn't really make a difference. Okay, that's it for today. 5 minutes late, I'm sorry. Enjoy it, have a nice day, have a nice week, and see you next Tuesday.